Today's topic, diffraction. It is the phenomenon of bending of light around corners of an object. So, light bends around the corners of an object. So, as a result, certain diffraction patterns are produced. So, the patterns are certain maximum and minimum. For secondary minimum, path difference is equal to a sine theta is equal to n lambda. That is the condition for secondary minimum. So the condition for minimum is a sine theta is equal to n lambda, where n is equal to 1, 2, 3, etc. Then for secondary maximum, path difference a sine theta is equal to 2n plus 1 lambda by 2, where n is equal to 1, 2, 3. So as a result of diffraction, minimum and maximum are produced. And the condition for minimum is a sine theta is equal to n lambda, and for maximum the condition is a sine theta is equal to 2n plus 1 lambda by 2. Problem: a slit of width a, so width of the slit is a, is illuminated by a monochromatic light of wavelength 6000 angstrom. So 1 angstrom is equal to 10 to the power minus 10 meter at normal incidence. So calculate A. So here we have to find out the slit width. Wavelength is given. It is monochromatic. Light is monochromatic. Wavelength is given. We have to find out the slit width. Then A, the first minimum falls at an angle of diffraction of 30 degree. So our equation, a sine theta is equal to lambda. So here first minimum, so n is equal to 1. So a sine theta is equal to lambda. Then from this, a is equal to lambda divided by sine theta. So lambda is equal to 6000. Angstrom is converted to meter. So 6000 times 10 to the power minus 10 divided by sine 30. So sine 30 is 1 by 2. Sine 30 1 by 2, therefore is equal to 6000 times 10 to the power minus 10 times 2. That is approximately 1.2 times 10 to the power minus 6 meter. So the slit width for a wavelength of 6000 angstrom is 1.2 times 10 to the power minus 6 meter. Then B, the first maximum at an angle of diffraction 30 degree. Angle of diffraction 30 degree. So here first maximum condition, a sine theta is equal to 2n plus 1 lambda by 2. So a sine theta is equal to 1.5 lambda. Then from this, a is equal to 1.5 times 6000 times 10 to the power minus 10 divided by sin 30, that is 1 by 2. The value is approximately 1.8 times 10 to the power minus 6 meter. Next problem. In a single slit diffraction experiment, first minimum for lambda 1 is equal to 660 nanometer coincides with the first maximum for lambda 2. So first minimum coincide with first maximum. So wavelength lambda 1 and lambda 2. Lambda 1 is given, we have to find out lambda 2. So first condition is first minimum coincide with first maximum. So the equation is lambda 1 is equal to 1.5 lambda 2. So from this lambda 2 is equal to lambda 1 upon 1.5 is equal to 660 nanometer divided by 1.5, approximately 440 nm, 440 nanometer. Next problem, a single slit of width A is illuminated by a monochromatic light of wavelength 600 nanometer. The value of A at theta is equal to 30 degree on the screen. So here we have to find out the slit width. So here monochromatic light is used, the wavelength is 600 nanometer, angle is equal to 30 degree. So we have to find out the slit width. So here condition is given, that is first minimum at 30 degree. First minimum at 30 degree. So the equation is for minimum A sin theta is equal to n lambda. Here n is equal to 1, that is first minimum. So A sin theta is equal to lambda. From this A is equal to 600 nm divided by sin 30 is equal to 1200 times nanometer. Next problem. The aperture of the objective is 24.4 centimeter. So aperture is given, that is the diameter of the objective lens is given. The resolving power of the telescope given, lambda is equal to 2440 angstrom. So wavelength is given, aperture is also given. So we have to find out the resolving power. So the resolving power of a telescope, RP is equal to D upon 1.22 lambda. So D is given, that is 24.4 centimeter converted to meter, that is 10 to the power minus 2 meter, upon 1.22 times 2440 times 10 to the power minus 10. The value is approximately 8.2 times 10 to the power 5. That is the resolving power of the telescope. So here aperture is given, wavelength is given, resolving power is equal to D by 1.22 lambda. So the resolving power of a telescope is D by 1.22 lambda. Next problem. The value of numerical aperture of the objective lens of a microscope is 1.25. So the numerical aperture is given, that is 1.25. Find the minimum separation between 2 points. That is, here we have to find out small d, that is the limit of resolution. Here lambda is given, lambda is 5000 angstrom. So here we have to find out the limit of resolution, that is D of the microscope. D is equal to 1.22 lambda upon 2 mu sine theta. Again is equal to 1.22 lambda divided by 2 into mu sine theta is Na, that is numerical aperture. So mu sine theta is equal to Na. So again substituting the values, 1.22 times 5000 times 10 to the power minus 10 upon 2 times 1.25. The value is approximately 0.24 times 10 to the power minus 6 meter. So this is the value of the limit of resolution of a microscope. Next problem. Calculate the limit of resolution of a telescope objective having a diameter of 200 centimeter if it has to detect light of wavelength 500 nanometer coming from a star. So here we are viewing a star through a telescope. So here we have to find out the limit of resolution. Limit of resolution, that is D. D is equal to wavelength is given and diameter of the aperture is also given. So here limit of resolution D is equal to 1.22 lambda upon D. D is the diameter of the aperture. Again is equal to, substituting the values, 1.22 times lambda 500 times 10 to the power minus 9, that is 1 nanometer is 10 to the power minus 9 meter upon D 200 times 10 to the power minus 2, that is 200 centimeter in centimeter. So centimeter is converted to meter by giving 10 to the power minus 2. So we get approximate value as 305 times 10 to the power minus 9 rad.